by electric field and the Coulomb's force directly between two charges is the same as far as the forces on charges are concerned, but we will see later that this is a conceptual advance. So let me just talk a bit about it. Let us look at a charge distribution and the force it applies on a charge q far away, and last time we saw that this force is given by integration dV over r minus r prime cubed, charge distribution rho r prime acting on q. What we learned in the last lecture is if there is a charge distribution given, let us say this is rho r prime, and I am calculating force on a charge q at a distance. So let us make this coordinate system. This is at vector r. So this is vector r, and this vector is given by r prime. The distance from here to here is, this vector is r minus r prime. Then the force on q is given as F is equal to 1 over 4 pi epsilon 0. Since this is charge q, I will put a q here. Integration, volume integral, rho r prime, r minus r prime over modulus r minus r prime cubed. Notice that this quantity here is actually 1 over r square, or 1 over the distance between the charges square. When I integrate this, then I am calculating force due to each small distribution, a small charge here, and adding it up, which was the principle of superposition we learnt earlier. The question we ask now is it that I always need the other charge to find the force, or this original charge distribution itself does something in the space so that the other charge q feels a force? Let us understand that. What we are going to now say is that this charge distribution given here, rho r prime, itself creates a field around it. That means it distorts something around it. It creates a lot of lines around it, so that if I put a charge somewhere, because of this whatever I have created, which I am going to call the electric field, a force is applied on this. So charge distribution is creating an electric field around itself, and I am going to denote it by E vector at r, so that when charge q is put in this field, the force on this charge is given as q times E r. So notice what we are saying is, even if this charge is not there, due to the presence of this original charge distribution, a field is created inside. By field we mean at every point there is a vector. At every point there is a vector pointing in a certain direction, and when I put an extra charge on this, it creates a force. Now, as far as calculating force on q is concerned, whether I think in terms of field or I think in terms of when these charges are brought together there is a force, it doesn't really make a difference. Then why am I introducing such an idea of a field? Is it real? Can I really check if there is a charge distribution, it creates this field around itself? We will see later in the course that it is a real quantity that is capable of propagating from one place to the other. So it's a real entity. So from now onwards, we are going to focus on the electric field produced by a charge distribution, because that is what really is a physical quantity, and later we will see that that is what really takes information from one place to the other, or it applies forces on a given charge. So what we are going to now talk about is the electric field. As I said just now, that given an electric field E at R, the force on a charge Q put there is going to be Q times this ER. That means, by definition, electric field is nothing but force per unit charge. Direction and magnitude both are equivalent to force per unit charge. So that is the way I am defining it mathematically, but conceptually it's an advance. As I said, what we are actually suggesting is, given a charge distribution Q, it is creating a field around itself. So there exists something around it that I am calling the electric field, and its direction and magnitude is given by the force it applies on a unit charge. So let us see. Therefore, given this distribution of charge, the electric field by definition at point R is going to be 1 over 4 pi epsilon 0 integration over this volume rho r prime over r minus r prime cubed times vector r minus r prime. Let's see what we are doing. We are taking this as the origin. I am calculating field at a point R due to this charge distribution here, and due to this small volume here, the electric field is given by, at a distance r minus r prime, it is given by 1 over 4 pi epsilon 0 dV rho r prime over r minus r prime cubed times r minus r prime, and due to this entire charge distribution I just integrate it over. This becomes the electric field by principle of superposition. For example, if I take a point charge, let us say at some position vector r, then the electric field at some other position r is going to be E equals 1 over 4 pi epsilon 0. This will be the vector from here to here. This will be r minus r is going to be q over r minus r cubed r minus r. And the way it is going to look, I am going to draw it in a different color, is all these lines, field lines, going away from this point charge. This is how I am going to denote it. So notice that field exists everywhere, because given a unit charge or given any charge anywhere around the point charge is going to experience a force. So by definition field exists everywhere, but that field exists independent of whether other charge is there or not. Even if that we do not feel any force, this charge by itself is creating a field. Let us look at a line charge. In one of the previous lectures we did a line charge of carrying lambda per unit length, and what we saw is that it creates a field like this around it. So anywhere around it I put a charge, it experiences a force. If I look at it from the top, let us look at it from the top. This is the line charge, the lines are all going out. As you go farther away, the field magnitude becomes smaller. So, I may sometimes indicate it by making smaller arrows. You go farther away, arrows become even smaller. So, by making these pictures, what I am making you feel is that something exists around a given charge, and that is what I am going to call electric field. And we have also seen how to obtain it from a given charge distribution. Are there other examples of fields? Let me just talk a bit about them so that you get a feeling for this. Other examples. Field. A very obvious example that you are familiar with is gravitational field. In which I can say that if there is a mass, it creates a gravitational field around it. So, something exists, that gravitational field exists because of this mass being somewhere, right? And given any other mass put here, it experiences a force F vector whose magnitude is given by m times this gravitational field, which we call g, gravitational acceleration. Another example of field is going to be, suppose there is a fluid flowing, and I try to see how the velocity of this fluid is changing. This may be coming out of a water tap here, and fluid may flow like this. So, you see at each point there is a different velocity associated with this water flowing out of the pipe. It obviously each one follows a trajectory like this, but at each point there is a velocity, and I can say there is a velocity field. I can also ask what is the mass per unit area per unit time flowing through any cross section here. Or a cross section here, and that is what is called current, which gives me the direction of flow as well as the amount of that fluid flowing. So, this current Jr is also a field, all right, which exists everywhere, is a vector quantity. So, these are some examples of the field. I have given you two examples of what electric field around two different charges looks like. By electric field